Good evening. Welcome back, or if you're new here, welcome. Tonight we're going to explore something that's been there since before there was an us to notice it. Something so constant, so ordinary in its daily appearance that we forget how extraordinary it actually is. We're going to discover the sun, not in a rush, not cramming facts, but slowly, calmly, moving through human history like watching shadows lengthen across ancient stones. We'll begin with our ancestors, who had no idea what the sun was but knew they needed it desperately. We'll stand with priests and philosophers as they theorized and worshipped. We'll witness the slow realization that Earth orbits the sun, not the other way around. We'll measure its vast distance, decode its light, and eventually understand the nuclear furnace at its heart. And we'll arrive, by the end, at modern knowledge that would seem like magic to those ancient sun worshippers. Complete understanding of the star that makes all life possible. This will take time. We're in no hurry. The sun itself has been shining for 4.5 billion years. We can spend one evening exploring it slowly. If this story helps you rest tonight, feel free to like or subscribe, though there's no pressure, truly. I'm always curious where you're listening from, so if you feel like it, comment your city and what time it is there. Perhaps you're watching the sun set right now, or maybe it rose hours ago on your side of the planet, or maybe it's the middle of the night and the sun is warming someone else's morning on the far side of the world. Dim the lights now, if they aren't already. Adjust your pillow. Maybe turn on a fan for gentle background noise, or simply let the silence settle around you like evening shadows. We have a long journey ahead, moving through millennia of human wonder and discovery, but we'll take it slowly, one sunrise at a time. Let's begin. Ancient sun worship. Before understanding. Imagine you are standing on Salisbury Plain in what will someday be called England, but that name doesn't exist yet. It's approximately 3000 BCE. The stones around you, Stonehenge, though that name doesn't exist yet either, cast long shadows in the pre-dawn darkness. The air is cold, bitingly cold, that particular chill of midwinter morning when breath mists and the ground crunches with frost under your feet. You can smell the dampness of the earth, the grass heavy with dew that will soon freeze. You're not alone. Around you stand others. People whose language you don't speak, whose lives are harder than you can imagine, whose entire existence revolves around patterns in the sky. They've gathered here, as they do every year, for the winter solstice, the darkest day of the year, the day when the sun reaches its lowest point, when daylight is shortest, when the fear that perhaps this time the sun might keep retreating, might not return, sits heavy in everyone's chest. The eastern horizon is beginning to lighten. Not sunrise yet, just the pre-dawn glow, that soft grey blue that comes before true light. The cold is almost painful now. Your fingers are numb. Everyone is facing east, watching, waiting. There's no chanting yet, just silence and collective anticipation and the sound of wind moving across the plain, rustling through winter-dead grass. And then, the first sliver of gold. The sun's edge appears exactly where the stones have been aligned to predict, exactly in the gap that generations of builders created for this moment. The light is thin at first, just a bright line on the horizon, but it's growing. You can feel it even before you see it. The first warmth of direct sunlight after a long, cold night. Someone begins to sing, a low chant in that unknown language, and others join in. The sound rises into the morning air, competing with the bird song that has also begun, birds greeting the return of light. With the bird song, the sun climbs higher. The shadows of the great stones shift, marking time the way they've been designed to do. The warmth increases. Not much, it's still midwinter, but enough to notice, enough to feel the difference between facing the sun and having your back to it. This is what their lives depend on: the sun's return, its warmth coaxing growth from planted seeds, its light making the difference between feast and famine. They don't understand what the sun is. They just know they need it, desperately, and they're relieved beyond words that once again it hasn't abandoned them. Time shifts now, carrying you forward and southward. You find yourself in ancient Egypt, perhaps 2500 BCE, standing in a temple dedicated to Ra, the sun god. It's just before dawn, and priests are preparing for the morning ritual, the daily ritual they perform every single day without fail, because the sun's rising is not guaranteed, they believe. It must be encouraged, coaxed, honoured. The temple is made of limestone blocks that still hold the coolness of night. Your feet on the stone floor feel the chill even through sandals. The air smells of incense, frankincense and myrrh burning in braziers, and of the Nile's muddy scent carried on the pre-dawn breeze. The priests are dressed in white linen, ritually purified, moving with practiced precision. They've done this ceremony every morning of their adult lives. Their fathers did it before them. Their sons will do it after. You walk with them to the temple's eastern opening. The Nile is visible in the distance, a dark ribbon reflecting the first hints of dawn light. The desert beyond is still shadowed. The chief priest holds a sistrum, a kind of sacred rattle, and begins to shake it, a dry metallic sound that breaks the morning silence. The chanting begins, hymns to Ra, prayers for the sun, God's safe journey across the sky, gratitude for his return from the dangerous underworld where he travels each night, battling the serpent Apophis who tries to prevent sunrise, and then Ra appears. The sun breaks the eastern horizon and the chanting intensifies. The light hits the temple, illuminating specific chambers that were designed to catch the dawn rays at particular times of year. The priest's white linen seems to glow. The limestone walls turn golden. The temperature rises noticeably as the sun climbs, that delicious warmth after the relative cool of night. You can feel the heat on your face, on your shoulders, the life-giving warmth that makes Egypt's crops possible despite the desert surrounding the Nile's green ribbon. This ritual happens every morning. Every single morning. The priests believe that their ceremonies help ensure the sun's return, that Ra needs their devotion and praise to have the strength to rise again. They don't know that the sun is a massive ball of fusing hydrogen 93 million miles away, operating by nuclear physics that would continue exactly the same with or without their prayers. They just know the sun is divine, essential, worthy of their highest devotion. The morning passes. You watch the priests go about their day, which is structured entirely around solar cycles. Morning prayers at dawn, mid-morning offerings when Ra is ascending, noon ceremonies when Ra reaches his zenith, his moment of maximum power, afternoon rituals as he begins his descent toward the western horizon, evening prayers as he disappears, beginning his perilous night journey through the underworld. The day is measured entirely by the sun's position. Time shifts again. You're in the Yucatan Peninsula now, perhaps 800 CE, standing in a Mayan city whose name is lost to us, but whose astronomical knowledge was remarkably sophisticated. The heat here is different from Egypt, humid rather than dry, the air thick with moisture, and the smell of tropical vegetation, the constant background buzz of insects. You're in an observatory, though it doesn't look like the domed buildings you might imagine. It's a stone structure with carefully positioned openings, windows that align with specific solar positions at specific times of year. A Mayan astronomer priest stands beside you, watching the afternoon sun with an intensity that suggests this is more than casual observation. He's tracking its position against markers on the horizon, checking calculations on a bark paper codex covered in intricate glyphs. The Maya have developed a calendar of remarkable accuracy. They know the solar year is approximately 365.24 days long, more accurate than the Julian calendar being used in Europe at this same time. They've determined this through generations of patient observation, marking where the sun rises and sets throughout the year, noting the solstices when it reaches its extreme northern and southern positions, recording equinoxes when day and night are equal length, calculating the cycles with mathematical precision. The astronomer makes a note in his codex. The glyphs are beautiful, each one a tiny work of art, but they're also functional, recording data, preserving knowledge. He's continuing work his teachers began, which their teachers began before them, a chain of observations stretching back centuries. Every day someone marks the sun's position. Every year the patterns repeat. Every generation refines the measurements slightly, improving accuracy, building a body of knowledge that will let them predict solar events decades into the future. The sun here is powerful, intense. This close to the equator, it's nearly overhead at noon, blazing down with heat that sends most people to shade during midday hours. The stone of the observatory is hot to the touch, storing solar heat and radiating it back. The shadow of the gnomon, a vertical stick used to mark the sun's position, shifts visibly across the courtyard floor as the afternoon progresses, a natural clock that anyone can read. Evening comes, as it always does. The sun descends toward the western horizon, and the sky turns orange, then red, then purple. The heat begins to break. The insect's evening chorus replaces the afternoon's buzzing. The Mayan astronomer finishes his day's observations, carefully storing his codex, knowing he'll repeat this same routine tomorrow, and the day after, and the day after that, continuing the ancient work of understanding the sun's movements. Let yourself drift forward through centuries now. You're with the Inca in the Andes, perhaps 1450 CE, attending a ceremony to Inti, the sun god. The altitude here makes the sun feel different, closer somehow, more intense, the thin air offering less protection from its rays. The morning is cold, as mornings at high altitude always are, but the sun's warmth is immediate when it crests the eastern mountains. The Inca have aligned their entire civilization around solar worship. The Sapa Inca, the emperor, is considered the son of Inti, divine royalty whose authority comes directly from the sun. Gold, which they call the sweat of the sun, covers temples and royal buildings, reflecting sunlight in dazzling displays. The Coricancha, the golden temple in Cusco, has walls literally covered in gold sheets, making the entire building shimmer when the sun hits it. The ceremony you're witnessing involves offerings, maize beer poured into ceremonial vessels, llamas sacrificed humanely quickly, textiles woven from the finest vicuña wool laid before the temple. The priests chant in Quechua, honouring Inti, asking for his continued blessings on the crops, on the empire, on the royal family. The rising sun illuminates the proceedings, turning the golden temple walls into a blazing beacon visible for miles. These people, like the Egyptians and the Maya and the builders of Stonehenge, understand the sun's importance without understanding its nature. They know the sun makes crops grow. They know its warmth is necessary for life. They know its daily and seasonal cycles with precision. They track the solstices, mark the equinoxes, organize their agricultural calendar around solar movements. But they don't know what the sun actually is. Don't know it's a star, don't know about fusion, don't know its immense distance or size. To them, it's divine, powerful, mysterious, necessary, worthy of their highest devotion and most careful observation. The daily rhythm of solar worship continues: dawn prayers, midday offerings, sunset ceremonies. Through all the ancient cultures that left records, and surely countless others that didn't, the pattern repeats. The sun is central. The sun is sacred. The sun's movements must be tracked, predicted, honoured. Life depends on it, even if no one understands why or how. Early philosophical understanding, Greek and Islamic astronomy. Now imagine you stand in ancient Greece, approximately 400 BCE. You're in Athens, in the academy founded by Plato, though Plato himself is old now, and his student Aristotle is beginning to develop his own ideas about the cosmos. The Mediterranean sun blazes overhead, hot and bright, casting sharp shadows across the columned courtyard where philosophers debate. The air smells of olive trees, of the dust that coats everything in Greek summer, of the limestone buildings baking in afternoon heat. You can hear the philosophers arguing, not angrily, but intensely, each trying to understand the nature of the heavens through pure reason. They don't have telescopes, don't have modern instruments, just their eyes and their minds and the records of observations passed down through generations. Anaxagoras of Clazomenae has recently been exiled from Athens, and his fate is part of what the philosophers are discussing. His crime? Suggesting that the sun is not a god but a hot stone larger than the Peloponnese. This idea that the divine sun might be a natural object, subject to natural laws, is considered heresy, dangerous, impious. The fact that he was exiled rather than executed might be considered merciful, but it serves as a warning. Some ideas about the sun are too radical for public consumption. Yet in the safety of the academy, philosophers continue to theorize. Aristotle is developing his model of the cosmos, Earth at the center, surrounded by concentric celestial spheres. The sun occupies one of these spheres, moving around Earth in a perfect circle, as do the moon, the planets, and the stars. It's a tidy model, elegant in its geometry, wrong in almost every detail, but remarkably influential. It will dominate European thinking for nearly 2,000 years. You watch as Aristotle walks through the courtyard, discussing his ideas with students. He points to the sun, not looking directly at it, of course, they've learned that lesson, and explains his reasoning. The sun must be perfect, unchanging, eternal, because it occupies the celestial realm beyond the moon. Below the moon is the sublunary realm, the world of change and decay where we live. Above the moon is perfection. The sun, being above the moon, must be made of quintessence, the fifth element, different from the earthly elements of earth, water, air, and fire. It's elegant philosophy, but it's not quite science. There's no systematic observation, no testing of predictions, no willingness to change the theory when observations don't match. But it's a step beyond pure mythology, an attempt to understand the sun through reason rather than just worship. Time passes, though not too far forward. You're elsewhere in the Greek world, perhaps on the island of Samos, around 270 BCE. Aristarchus of Samos is making observations and calculations that won't be fully appreciated for nearly 2,000 years. He's trying to determine the sun's distance and size using geometry and careful observation. The method is clever. During a lunar eclipse, watch how long it takes the moon to pass through Earth's shadow. By measuring this and comparing it to the moon's apparent size, you can calculate the relative sizes of Earth, moon, and sun. During a quarter moon, measure the angle between the sun and moon. With geometry, you can determine their relative distances. The mathematics is complex but elegant, pure geometry applied to the cosmos. Aristarchus concludes that the sun is much larger than Earth, perhaps 20 times wider, and much farther away than the Moon. His distance estimate is too small by a factor of 20, but the attempt itself is revolutionary, treating the Sun as a physical object that can be measured rather than a divine mystery. Even more radically, Aristarchus suggests that if the Sun is so much larger than Earth, perhaps Earth orbits the Sun rather than vice versa. It's a heliocentric model proposed 1,800 years before Copernicus, but almost no one believes it. It seems absurd. We can feel that we're standing still, after all. Surely if Earth were moving, we'd notice. The centuries pass. You find yourself now in the Islamic Golden Age, perhaps in Baghdad in 830 CE, in the House of Wisdom. This is a remarkable place, a library, an observatory, a translation centre where Greek and Indian and Persian knowledge is being preserved, studied and expanded. Europe is in its so-called Dark Ages, but here astronomy flourishes. The smell is of paper and ink, expensive materials carefully used. The observatory has brass instruments polished to gleaming, astrolabes for measuring star positions, quadrants for measuring solar altitude, sundials of exquisite craftsmanship. The astronomers here are making observations of remarkable precision, measuring the length of the solar year to within minutes of the modern value, charting the Sun's path through the zodiac, improving on Greek and Indian astronomical tables. You watch as an astronomer named Al-Battani makes careful observations of the Sun at noon. He's using a large quadrant mounted on a stable wall aligned precisely north-south. As the Sun reaches its highest point, he measures its altitude above the horizon with remarkable precision. He does this day after day, season after season, year after year, building a record of how the Sun's noon altitude changes throughout the year. The work is patient, meticulous, unglamorous, just daily measurements, carefully recorded, slowly accumulating into knowledge. The routine never varies. Morning setup of instruments, noon observation when the Sun crosses the meridian, afternoon calculations checking the data, evening recording in permanent tables. The work spans decades, sometimes generations, each astronomer adding to the accumulated observations of their predecessors. They're refining the solar calendar, determining the exact length of the year, improving the ability to predict eclipses and calculate religious dates. It's practical astronomy in service of religion and agriculture and navigation, but it's also knowledge pursued for its own sake. The Islamic astronomers develop sophisticated mathematical techniques, trigonometry applied to celestial observations, interpolation methods for their tables, calculations of remarkable complexity performed without modern notation or calculators, just patient arithmetic and geometric thinking. They translate Ptolemy's Almagest, the great Greek astronomical work, and don't just preserve it, they improve it, correct errors, add new observations, extend its tables. In Cairo, in Cordoba, in Samarkand, observatories operate continuously. In Cordoba, scholars correspond, sharing observations, debating interpretations, slowly building a comprehensive understanding of the Sun's movements. They measure the solar day precisely, determining that the Sun returns to the same position in the sky in exactly 24 hours on average, though the actual solar day varies slightly throughout the year due to Earth's elliptical orbit and tilted axis, though they don't phrase it that way. They notice that noon sundial shadows fall slightly differently than their tables predict, and they refine their understanding of solar motion to account for this. The Sun to them is still a divine creation, but it's also a natural phenomenon that follows regular, predictable laws. They're developing a kind of proto-scientific approach: observation, measurement, mathematical modelling, prediction, refinement. The sun isn't arbitrary or capricious. It moves in precise patterns that can be calculated and predicted. This is a profound insight, even if they don't yet understand why the patterns exist. Centuries accumulate. The knowledge preserved and advanced in Islamic centres slowly makes its way back to Europe, through translation centres in Spain and Sicily, through scholars who study Arabic texts and bring the learning north. The Dark Ages are ending. The Renaissance is beginning. And the stage is set for a revolution in understanding, not just of the sun's movements, but of humanity's place in the cosmos. The Copernican revolution, recentering the universe centuries pass. You find yourself in Renaissance Europe, specifically in Frauenburg, Poland, in the early 1500s. You're in a tower room that serves as both living quarters and observatory for a church canon named Nicholas Copernicus. The room smells of candle wax and parchment and the particular mustiness of old books. Through the window you can see the Baltic coast in the distance, but right now you're looking at papers covered in calculations. Copernicus works by candlelight, though he tries to conserve expensive candles by working mostly during daylight hours. The papers on his desk contain something revolutionary, something dangerous. Mathematical proof that Earth orbits the Sun, not the other way around. He's been working on this for decades, quietly, sharing his ideas only with a few trusted friends. The full manuscript, De Revolutionibus Orbium Coelestium, on the revolutions of the celestial spheres, is nearly complete, but he's reluctant to publish it. The reluctance isn't cowardice, it's pragmatism. The Catholic Church has spent centuries teaching that Earth is the centre of creation, the focus of God's attention, the unmoving foundation of the cosmos. Suggesting otherwise seems to diminish humanity's importance, to contradict Scripture, to upset the entire philosophical and theological order. Copernicus knows his ideas will be controversial. He's a church official himself, he understands the stakes. But the mathematics are compelling. By placing the sun at the centre with Earth and the planets orbiting around it, the motions of the planets become simpler, more elegant. The strange retrograde loops that planets trace against the background stars, when they seem to stop, reverse direction, then resume forward motion, make perfect sense in a heliocentric model. They're just what you'd see from a moving platform, Earth, watching other platforms, planets, orbit at different speeds. In the old geocentric model, explaining retrograde motion required elaborate epicycles, circles upon circles, mathematical tricks to save the appearances. Copernicus's model is cleaner, more beautiful, and beauty in mathematics often indicates truth. He's not the first to propose heliocentrism. Remember Aristarchus in ancient Greece. But he's the first to develop it fully, mathematically, with detailed tables of planetary positions. The work is thorough, careful, the culmination of decades of observation and calculation. But it sits on his desk, unpublished, too dangerous to release. Only on his deathbed in 1543 does Copernicus finally allow publication. Legend says the first printed copy was placed in his hands as he died, though he was probably unconscious and never saw it. The book enters the world quietly, initially causing less controversy than expected, because most readers think it's just a mathematical trick for calculation, not a claim about physical reality. The real fight will come later. Time shifts forward a few decades. You're in Padua, Italy, in 1609. Galileo Galilei, a mathematics professor, has heard about a Dutch invention, a spyglass that makes distant objects appear closer, and has built an improved version. He's pointing it at the night sky, and what he sees will change history. The moon, viewed through his telescope, is not the perfect crystalline sphere that Aristotle claimed. It has mountains and valleys. You can measure their height from the shadows they cast. The Milky Way is not a nebulous glow, but countless individual stars. Jupiter has moons, 4 visible ones at least, orbiting around it, proving that not everything orbits Earth. And Venus shows phases, like a miniature moon, which proves it must orbit the Sun, not Earth. The observations are devastating to the old world view. You stand with Galileo in his study, which smells of ground glass and metal polish from telescope construction, and of the oil lamps that light his evening observations, as he sketches what he's seen. His drawings will be published in Sidereus Nuncius, the Starry Messenger, in 1610, and will create a sensation. Here is observational evidence, not just mathematical elegance, supporting the Copernican model. The Catholic Church initially doesn't react harshly. Some Jesuit astronomers confirm Galileo's observations using their own telescopes. There's intellectual excitement, debate, discussion. But as Galileo becomes more vocal, more insistent that the heliocentric model is physical reality and not just mathematical convenience, as he writes books in Italian rather than Latin to reach a broader audience, as he appears to mock the Pope in one of his dialogues, the institutional resistance hardens. You're present, though at a distance, because you're not important enough for close access, at Galileo's trial in 1633. The hall is formal, intimidating, filled with church officials in their robes. Galileo, old now and not well, stands before the Inquisition. The verdict is predetermined. He must recant, must state that his teaching of Earth's motion was wrong, must promise to abandon these ideas. The alternative is torture, imprisonment, death. Galileo recants. He has no choice, really. Legend says that as he leaves he mutters, "Eppur si muove," and yet it moves. But this is probably apocryphal. More likely he stays silent, accepting his house arrest, and spends his remaining years working on other problems in physics and mechanics. But the heliocentric model doesn't die with Galileo's recanting. The observations are real, the mathematics work. Other astronomers across Europe, Protestant and Catholic, establishment and rebel, continue the work. Johannes Kepler in Germany determines that planets orbit in ellipses, not circles, and discovers the mathematical laws describing their motion. Isaac Newton will later explain why, developing his law of universal gravitation that shows the Sun's gravity holding the planets in orbit. The Sun has been demoted from deity to astronomical object, but promoted from orbiting Earth to being the centre around which Earth and the planets revolve. The philosophical implications are enormous and unsettling. Earth is not the centre of creation. We orbit the Sun, which is presumably just another star, one of countless stars scattered through space. We are not special. Our planet is just one of several, not particularly remarkable. This is simultaneously humbling and liberating. Humbling because we're less cosmically important than we thought, liberating because the universe is vastly larger and more interesting than the old model suggested. The daily experience of sunrise hasn't changed. The sun still rises in the east, arcs across the sky, sets in the west, creating the same cycle that ancient sun worshippers observed. But the meaning has changed. We now know we're on a spinning planet orbiting a star, experiencing sunrise because our piece of the planet is rotating into view of the sun, not because the sun is rising to greet us. The subjective experience is identical. The objective reality is transformed. Understanding solar distance and size, measuring the immeasurable time, moves forward. You stand in the age of enlightenment now, the 1700s, when science is becoming respectable, when measurement and observation are replacing pure reason, when the question, how do we know, is as important as what do we know? You're at an observatory in France, perhaps the Paris Observatory, preparing for the transit of Venus across the Sun's face. This is June 6th, 1761, and astronomers across the world, in France, England, Russia, colonies, in the East and West Indies, are coordinating observations. The goal is to use this rare event to measure the Sun's distance precisely. The method, proposed by Edmund Halley, is ingenious. As Venus crosses the Sun's disk, observers at different latitudes will see it track across slightly different paths, an effect of parallax, the apparent shift in position when viewed from different locations. By timing exactly when Venus enters and leaves the Sun's disk from multiple locations, and knowing the distances between those locations on Earth, you can triangulate Venus's distance. And once you know Venus's distance, you can use Kepler's laws to calculate the distance to the Sun. The preparation is meticulous. Precise clocks, pendulum chronometers, the best available, are calibrated and recalibrated. Telescopes are aligned and tested. Solar filters, dark glass that allows safe viewing of the Sun, are prepared. The observers rehearse their procedures, noting exact times of contact as Venus's disk touches the Sun's edge, watching for the black drop effect that makes the moment of contact ambiguous, recording everything with precision. The day arrives. You're watching through the telescope, which smells of brass polish and feels warm even though it's morning. The Sun heats metal quickly. The filtered Sun appears as a perfect bright disk. And then, at the predicted time, a small dark circle begins to encroach from the edge. Venus, tiny compared to the Sun, begins its transit. It takes hours. Venus moves slowly against the Sun's vast disk, and throughout, observers note times, measure positions, record data with the best precision their instruments allow. The observations from around the world are eventually compiled, compared, calculated. The parallax is tiny, the measurements difficult, but the result is clear. The Sun is approximately 93 million miles away. 93 million miles. The number is so large it's almost meaningless. Light takes 8 minutes to travel that distance. No human technology of the era could cover it in a lifetime of travel. The Sun is incomprehensibly far away. And if the Sun is that far away, yet still appears as a disk in our sky rather than a point like the stars, then the Sun must be enormous. The calculation is straightforward. Knowing the distance and the angular size, you can calculate the actual diameter. The result: the Sun is about 109 times wider than Earth. Not 20 times, as Aristarchus estimated, but 109 times. If Earth were a marble, the Sun would be a beach ball. If the Sun were hollow, you could fit more than 1 million Earths inside. These numbers emerge slowly, refined over decades of additional observations. The transit of Venus method is repeated in 1769, with Captain Cook sailing to Tahiti to observe other expeditions scattered across the globe. Each set of observations adds precision, narrows the uncertainty. The astronomical unit, the Earth-Sun distance, becomes one of the fundamental measurements of astronomy, the yardstick by which all other cosmic distances are eventually measured. You stand in an observatory now in the 1770s, perhaps Greenwich in England. The workday begins before sunrise, arriving in the pre-dawn cold, unlocking the observatory dome, checking the instruments that have been carefully positioned the night before. The telescope is a beautiful piece of engineering. Brass fittings polished to a gleam, the tube itself a long cylinder mounted on an equatorial mount that allows smooth tracking of celestial objects. The smell is of metal and oil, the faint mustiness of the wooden building, the morning dampness that collects on metal surfaces overnight. As the sun rises, the observer waits. Direct solar observation requires proper filters, and even with dark glass, you never look through the telescope when the sun is too close to the horizon. The risk of accidentally catching unfiltered sunlight is too great. Better to wait until the sun is well risen, then use the projection method, letting the telescope focus the sun's image onto a white screen where it can be safely observed and measured without looking through the eyepiece at all. The daily routine is meditative in its repetition, adjusting the telescope to track the sun, watching its disk projected onto the screen, sketching any sunspots visible that day, measuring their positions relative to the sun's edge, noting the time with the observatory's precision clock. Each observation is recorded in leather-bound logbooks with pages of careful handwriting, columns of numbers, sketches of the sun's disk with spots marked. Years of data accumulate. 1770, 1771, 1772. Each year adding another layer to the archive, another set of observations that might reveal patterns or answer questions that haven't even been asked yet. The summer observations are different from winter, not because the sun changes, but because the observer's experience does. Summer mornings are warm, pleasant, the observatory comfortable even at dawn. The sun climbs high, reaching overhead by noon, its light intense and bright. Winter mornings are brutal. Arriving before dawn means arriving in bitter cold. Fingers numb even with gloves, breath misting in the frozen air. The sun's noon altitude is much lower in winter, its light weaker, its warmth insufficient to truly warm the day. Yet the observations continue, day after day, season after season, the patient work of astronomy proceeding regardless of weather or comfort. The implications sink in slowly as you stand in the observatory in the evening, the calculations spread out on a desk. The sun is not just bigger than Earth, it dwarfs Earth. The scale of the solar system is vastly larger than anyone imagined. And yet, despite being so massive and so distant, the sun's light and warmth reach us, sustaining all life on our tiny planet. The ancients were right to worship it, even if they didn't understand why. We do depend on the sun, absolutely. We're just beginning to understand the scale of what we depend on. The routine of solar astronomy has become more sophisticated now. Observatories are permanent structures staffed by professional astronomers who work to regular schedules. Morning observations of the sun's position, checking its altitude at noon with precision instruments, evening calculations refining the numbers. The work is patient, incremental, building on centuries of accumulated knowledge. Each generation of astronomers adds slightly more precision, corrects small errors, extends understanding a bit further. Solar eclipses become opportunities for observation rather than just cosmic events to fear or celebrate. You're present at a total solar eclipse now. The date is 1842 in southern France. The moon is slowly moving across the sun's face, the sky darkening in the middle of the day, the temperature dropping noticeably as the sun's warmth is cut off. Birds fall silent, confused by the artificial dusk. And then, for a few precious minutes of totality, the sun's corona becomes visible. The corona is the sun's outer atmosphere, usually invisible because the bright photosphere, the sun's visible surface, overwhelms it. But during totality, with the photosphere blocked by the moon, the corona appears, a pearly white glow surrounding the darkened disk, with streamers and loops extending outward, structured by magnetic fields no one understands yet. It's beautiful, eerie, inspiring. Astronomers sketch it quickly, trying to capture details before the few minutes of totality end, and the sun's photosphere reappears, overwhelming the corona's delicate light. The observations are puzzling. The corona is clearly part of the Sun, but its structure changes from eclipse to eclipse. Sometimes the streamers are symmetrical, sometimes asymmetrical. Sometimes they extend far into space, sometimes they're more compact. The Sun, it seems, is not unchanging and perfect as Aristotle claimed. It has an outer atmosphere that changes, that has structure and dynamics. But what causes this? What is the corona made of? Why is it visible only during eclipses? These questions will take decades to answer. As the 1800s progress, solar astronomy becomes increasingly sophisticated. Permanent solar observatories are built, equipped with specialized telescopes designed for safe solar viewing. Astronomers map sunspots, dark regions on the Sun's surface that appear and disappear in patterns no one yet understands. They measure the Sun's rotation by watching sunspots move across the disk. The Sun rotates once every 27 days or so, though different latitudes rotate at slightly different rates, which is puzzling. The Sun is not solid like Earth. It's something else, something that rotates differentially, something gaseous or liquid, or something not quite either. The daily routine of solar observers becomes standardized. Morning observations sketching sunspot positions, noon measurements of the Sun's altitude and diameter, afternoon calculations and data recording, years of observations slowly accumulating into understanding. The work is unglamorous but essential, laying the groundwork for discoveries that will come when new tools, spectroscopy, photography, later space-based telescopes, reveal the Sun's nature more fully. But even without understanding what the Sun is made of or how it shines, even without knowing about fusion or plasma or solar wind, astronomers of the 1800s have accomplished something remarkable. They've measured the Sun's distance and size, proved that Earth orbits the Sun and not vice versa, shown that the Sun is not perfect and unchanging, but has features that change over time. The Sun is no longer a god or a mystery. It's an object that can be studied, measured, understood through patient observation and careful reasoning. Remember those ancient sun worshippers at Stonehenge, watching the solstice sunrise with wonder and fear? Now astronomers measure the Sun's distance to millions of miles, calculate its size to within a few percent, predict its position centuries in advance. The journey from worship to understanding is profound, and yet the Sun itself remains what it always was, a vast, bright, warm presence in the sky, sustaining life, defining days and seasons, the centre of our small corner of the cosmos. The facts have changed. The fundamental relationship, humanity depending on the Sun, has not. Through the 1800s, solar observations continue to refine. Astronomers develop better instruments, more accurate clocks for timing observations, larger telescopes with finer optics, improved methods for measuring angles and distances. The Sun's diameter is measured more precisely. Its apparent motion through the zodiac is charted in detail. The equation of time, the discrepancy between solar time and clock time caused by Earth's elliptical orbit, is calculated accurately enough for practical navigation. The Sun transitions from mystery to measured object, from deity to data. The story continues, but we'll pause here for now. The circuits in your brain are quieting as you settle toward sleep. The Sun itself, somewhere on the other side of the world, from you at this moment, continues shining steadily as it has for billions of years, as it will for billions more. Rest now, while the patient work of understanding continues, one observation at a time, one calculation at a time, slowly revealing the nature of the star that makes everything possible. Decades pass. Imagine you stand in a laboratory in Germany, 1859. The room smells of chemicals, solutions of various salts dissolved in alcohol, stored in glass bottles with handwritten labels. There's the metallic scent of brass instruments being polished, the faint sulphur smell from matches used to light the gas lamps. Sunlight streams through a tall window, and in that sunlight something remarkable is about to be revealed. Josef von Fraunhofer, a glassmaker and optician, has been studying sunlight for years, trying to improve the quality of optical glass. He's discovered that by passing sunlight through a prism, splitting it into its component colours, like Newton did centuries before, and examining the resulting spectrum carefully through a telescope, you can see something unexpected. Dark lines crossing the rainbow. Hundreds of them, thin dark lines at specific wavelengths, like a barcode written in light. You watch as he demonstrates. The apparatus is elegant. Sunlight enters through a narrow slit, passes through a glass prism that spreads it into a spectrum, and is viewed through a small telescope that magnifies the spectrum enough to see details. The rainbow is beautiful, red blending to orange, to yellow, to green, to blue, to violet, but it's the dark lines that are puzzling. Why should sunlight have gaps in it? Why are specific colours missing? The lines are always in the same places. Fraunhofer has catalogued hundreds of them, labelling the most prominent with letters. The D lines in the yellow, the C and F lines in the red and blue, others scattered throughout the spectrum. The pattern is consistent, day after day, year after year. Whatever causes these lines is fundamental to the sun's nature. Time shifts forward a few decades. You're in a different laboratory now, this time in Heidelberg, Germany, in the 1850s. Gustav Kirchhoff and Robert Bunsen, yes, the Bunsen of the Bunsen burner, are conducting experiments that will decode Fraunhofer's dark lines. The laboratory smells of burning chemicals and hot metal, the distinctive odours of experimental chemistry. They've discovered something crucial. When you heat a chemical element to glowing, sodium, say, or calcium, or iron, it emits light at very specific wavelengths. Sodium gives a characteristic yellow glow. Calcium produces specific lines in the red and green. Each element has its own spectral signature, as unique as a fingerprint. And here's the key insight. If you pass white light through a cool gas of the same element, the gas absorbs light at exactly the same wavelengths it would emit if heated. It creates dark absorption lines in the spectrum. The implication is staggering. The dark lines in the sun's spectrum are absorption lines created by cooler gases in the sun's outer layers, absorbing specific wavelengths from the bright light generated in the sun's interior. By matching the dark lines to known elements heated in the laboratory, you can determine what the sun is made of. You can analyse the composition of something 93 million miles away without ever touching it, simply by examining its light carefully. The work begins. Careful spectroscopy of sunlight, heating every known element in the laboratory to see what lines it produces, matching laboratory spectra to solar spectra. Sodium is present. Those strong D lines match perfectly. Iron is abundant. Dozens of iron lines throughout the spectrum. Calcium, magnesium, chromium, nickel, cobalt, all detected through their characteristic absorption patterns. The sun, it turns out, is made of the same elements as Earth. Not divine quintessence, as Aristotle thought, but ordinary matter, iron, calcium, sodium, all the familiar elements of chemistry. But wait, there are lines in the solar spectrum that don't match any known element. In 1868, during a total solar eclipse, astronomers observed the spectrum of the chromosphere, the thin layer above the sun's visible surface, and see a bright yellow line that doesn't correspond to any element in the periodic table. The line is labelled D3, close to the sodium D lines, but distinctly different. The French astronomer Jules Janssen sees it. So does the English astronomer Norman Lockyer. They realise this must be a new element, one that exists in the Sun but hasn't been found on Earth. Lockyer names it helium, after Helios, the Greek sun god. An element discovered in the Sun before being found on Earth. Though ancient Egyptians worshipped Ra daily, they understood less about the Sun's nature than modern school children. But the Sun still had secrets to teach humanity, still contained substances we'd never encountered. Helium won't be isolated on Earth until 1895, nearly 3 decades after its solar discovery, when it's found in a uranium mineral. And helium turns out to be not just rare but important. The second most abundant element in the universe, a byproduct of the nuclear fusion that powers stars, though that won't be understood for another 50 years. You stand now in the routine of spectroscopic solar observation, a daily practice that develops through the late 1800s. Observatories dedicated to solar physics are built, equipped with spectrographs designed specifically for analysing sunlight. The morning routine. Arrive at the observatory, uncover the telescope, align the instrument to catch sunlight, carefully adjust the slit width for optimal spectral resolution, observe and photograph the spectrum, note any changes or anomalies, carefully log the data. The work is patient, meticulous. Photographing spectra requires long exposures, minutes sometimes, holding the telescope steady on the Sun, letting the light accumulate on the photographic plate. The plates are developed in dark rooms that smell of chemical developers and fixers, examined under magnification to identify and measure specific lines. Over time, a library accumulates, thousands of spectral lines catalogued, their wavelengths measured precisely, their intensities noted, their corresponding elements identified. The darkroom work has its own rhythm and ritual. The spectroscopist enters after allowing eyes to adjust to darkness, working by dim red safe light that doesn't expose the photographic plates. The smell is distinctive: acetic acid from the stop bath, sodium thiosulfate from the fixer, the slightly musty odour of the darkroom itself. Plates are immersed in developer solution, rocked gently, watched for the ghost of the spectrum to appear, gradually darkening. Too short and the spectrum is faint, hard to measure. Too long and it's overexposed, details lost. The timing must be exact, learned through experience. Once fixed and washed and dried, the plates are examined under a measuring microscope in proper light. Each dark line must be identified, its position measured to within micrometers, its wavelength calculated from the known dispersion of the spectrograph. This work can take hours for a single spectrum, measuring, calculating, comparing with reference tables, noting matches and puzzles. A day's observation might yield one spectrum. A year's work might produce a catalogue of a few dozen carefully measured spectra. The accumulation is slow but steady, each observation adding to the growing understanding. Different observatories develop specializations. Some focus on sunspot spectra, others on the quiet sun, others on the flash spectrum visible during eclipses. The data are shared through publications and correspondence, observatories building on each other's work. The international collaboration, still informal but growing, creates a collective effort larger than any individual observatory could achieve. Letters cross oceans, carrying reports of new spectral discoveries, observations confirming or questioning earlier results, the slow conversation of science conducted at the pace of sailing ships and later telegrams. The Sun reveals its chemistry through this work. Hydrogen is the most abundant element. The strongest absorption lines in the visible spectrum are the Balmer lines of hydrogen, though this won't be fully understood until quantum mechanics explains atomic structure. Helium is also very abundant. Iron and the other metals are present, but in much smaller quantities. The Sun is mostly hydrogen and helium, with traces of everything else. But spectroscopy reveals more than just chemistry. By observing spectra from different parts of the Sun's disk, centre versus edge, different latitudes, sunspots versus quiet regions, astronomers discover that the Sun's surface is not uniform. Sunspots are cooler than surrounding areas, their spectra show it. Different regions have slightly different compositions or temperatures or motions. The Sun is not a simple, uniform sphere. It has structure, variation, complexity. Some astronomers even notice that spectral lines are slightly shifted, toward the red at one edge of the Sun, toward the blue at the opposite edge. This is the Doppler effect. Light from a source moving away from you shifts to longer wavelengths, redward, while light from an approaching source shifts to shorter wavelengths, blueward. The shifting lines prove that the Sun is rotating, with one edge spinning toward us and the other away. The rotation period is measured, about 25 days at the equator, slower at higher latitudes. The Sun rotates differentially because it's not solid, it's gaseous or something fluid, with different latitudes rotating independently. How does the Sun shine? The mystery of solar energy. But spectroscopy, for all its revelations about solar composition, doesn't answer a more fundamental question. How does the Sun shine? What provides the energy that's been radiating into space without apparent decrease for the entire span of human history, and presumably much longer? You find yourself pondering this mystery alongside scientists in the mid-1800s. The Sun clearly produces enormous amounts of energy. It bathes the Earth in light and heat, and Earth intercepts only a tiny fraction of the Sun's total output, about 1 part in 2 billion. The total energy radiated by the Sun is staggering, approximately 400 trillion watts, a number so large it's meaningless without context. But where does this energy come from? The obvious answer: combustion. The Sun, burning like a gigantic coal fire, fails immediately upon calculation. If the Sun were made of coal and oxygen, burning at the maximum possible rate, it would consume itself completely in just a few thousand years. Geological evidence clearly shows Earth is far older than that. Fossils of ancient organisms, sedimentary rock layers thousands of feet thick, erosion patterns that require millions of years. The Earth is ancient, which means the Sun must be ancient too, and any energy source powering it must last, for geological timescales at minimum. Lord Kelvin, one of the preeminent physicists of the 1800s, proposes an alternative: gravitational contraction. Perhaps the Sun is slowly shrinking, converting gravitational potential energy into heat as it contracts. The calculation is straightforward. Calculate the gravitational energy available if the Sun contracts from infinite diffuseness to its current size, divide by the current rate of energy output, and you get the maximum age the Sun could have been shining. The result: approximately 20 to 30 million years. That's how long gravitational contraction could power the Sun. Kelvin considers this a reasonable age for the Sun, and by extension for Earth. 20 million years seems like a long time, certainly long enough for geological processes observed today to have shaped the planet. But there's a problem. Geologists, examining rock formations and calculating erosion rates and studying fossil sequences, argue that Earth must be far older than 20 million years. Charles Darwin's theory of evolution by natural selection, published in 1859, requires many millions of years for species to evolve from common ancestors. Geologists studying mountain building and erosion suggest hundreds of millions of years might be needed. The evidence from multiple fields points toward an ancient Earth, But the physics of the sun seems to limit its age drastically. The conflict is real and frustrating. You can feel it in scientific meetings and published papers, the tension between physicists certain of their calculations and geologists certain of their observations. Kelvin dismisses the geologist's evidence, confident that physics constrains what's possible. The geologists point to rocks and fossils, insisting the Earth must be old regardless of what calculations about the sun suggest. The impasse is complete. Imagine sitting in a scientific society meeting in London, perhaps 1895. The room is wood-panelled, lit by gas lamps filled with men in formal Victorian attire. Women scientists are rare in this era, their contributions often unrecognised or attributed to male colleagues. The air smells of pipe smoke and wool suits and the coal fires heating the building. Lord Kelvin himself is present, elderly now but still commanding respect. His calculations about the sun's age treated as near gospel truth by many physicists. A geologist presents evidence. Fossil sequences showing gradual evolution, sedimentary deposits thousands of feet thick that must have taken immense time to accumulate, erosion patterns in river valleys that require millions of years at current rates. The calculations point toward hundreds of millions of years, perhaps even a billion. The physics, Kelvin responds, simply doesn't allow it. The sun cannot shine that long on known energy sources. One or the other must be wrong, and he's confident it's not the physics. The debate continues for years, growing increasingly heated as better geological evidence accumulates, but the physics remains unchanged. Some scientists suggest perhaps the laws of physics are different in stars, though this seems desperate. Others propose that Earth might have additional internal heat sources beyond what Kelvin calculated. A few quietly wonder if perhaps there's some unknown energy source, but what could it be? Chemistry is well understood. Gravity is well understood. What else is there? The answer, it turns out, requires physics that doesn't yet exist in the 1800s. The sun is not burning chemically. It's not contracting gravitationally, at least not as its primary energy source. It's doing something else entirely, something that won't be understood until the 20th century brings revolutionary new physics, relativity, and quantum mechanics. Nuclear fusion. The answer emerges. Time shifts. You stand now in the early 20th century, in the aftermath of Einstein's miraculous year of 1905. One of Einstein's papers that year introduced special relativity and contained the famous equation E equals mc squared. Energy equals mass times the speed of light squared. The equation says that mass and energy are equivalent, that mass can be converted to energy and vice versa, that even a tiny amount of mass represents an enormous amount of energy because the speed of light is such a large number. The speed of light is approximately 300,000 kilometers per second. Square that. 90 billion kilometers squared per second squared, or in more standard units, 90 quadrillion meters squared per second squared. Multiply even a tiny mass by that factor, and you get tremendous energy. 1 kilogram of mass, if fully converted to energy, would yield 90 petajoules, enough energy to power a large city for weeks. But Einstein's equation is theoretical. Is there any natural process that actually converts mass to energy? Nuclear physics, still in its infancy, begins to suggest possibilities. Radioactivity, discovered by Henri Becquerel in 1896 and studied extensively by Marie and Pierre Curie, shows that atomic nuclei can spontaneously decay, releasing energy in the process. Nuclear reactions release millions of times more energy per atom than chemical reactions. Perhaps something nuclear powers the sun. In 1920, Arthur Eddington, a British astrophysicist, makes a bold suggestion. He's been calculating the conditions in the Sun's interior, the temperature and pressure needed to support the Sun against its own gravity, and realises the core must be extraordinarily hot and dense, perhaps hot enough for atomic nuclei to fuse together. Hydrogen is the most abundant element. Helium is the second most abundant. 4 hydrogen nuclei could fuse to make one helium nucleus, and the helium weighs slightly less than the 4 hydrogens combined. That missing mass, converted to energy via Einstein's equation, could be the Sun's power source. The numbers work beautifully. The mass deficit is small, about 0.7% of the hydrogen mass. But multiplied by the enormous factor of c squared, it yields tremendous energy. Fusing 600 million tons of hydrogen per second, losing about 4 million tons per second to energy conversion, the Sun could shine at its observed luminosity for billions of years. Billions, not millions. Long enough for geology, for evolution, for Earth's ancient age to be accommodated comfortably. But can fusion actually happen? Hydrogen nuclei are protons positively charged, and positive charges repel each other through electromagnetic force. To fuse, 2 protons must get close enough for the strong nuclear force, which operates only at extremely short range, to overcome the electromagnetic repulsion and bind them together. The calculations show this requires temperatures of millions of degrees. Even in the Sun's core, nuclei are moving too slowly, on average, to overcome the electromagnetic barrier. The answer comes from quantum mechanics. George Gamow and others in the late 1920s realized that quantum tunneling makes fusion possible at lower energies than classical physics would require. Particles have wave-like properties. A proton approaching another proton doesn't just bounce off if it lacks sufficient energy. There's a small but non-zero probability it can tunnel through the electromagnetic barrier, like a ghost passing through a wall. The probability is tiny for any individual collision, but in the Sun's core, with countless trillions of collisions happening every second, quantum tunneling makes fusion occur at a sufficient rate to power the Sun. Hans Bethe, in 1938, works out the detailed chain of reactions. The proton-proton chain, as it's called, is a sequence of nuclear reactions that ultimately converts 4 hydrogen nuclei into one helium nucleus plus energy. The first step is the hardest, 2 protons fusing to make deuterium, heavy hydrogen, with 1 proton converting to a neutron via the weak nuclear force, releasing a neutrino and a positron. This step is extraordinarily slow. Any given proton in the Sun's core will wait, on average, billions of years before successfully fusing with another proton. But the Sun contains so many protons that enough fusions happen each second to power it. Once deuterium is formed, the subsequent steps are faster. Deuterium fuses with another proton to make helium-3. 2 helium-3 nuclei fuse to make helium-4, releasing 2 protons in the process. The net result, 4 hydrogens become 1 helium, 2 neutrinos are released, and energy is generated through the mass deficit. This is the proton-proton chain, the dominant fusion process in the Sun and stars of similar mass. You stand now in the abstract world of nuclear physics, imagining the Sun's core. The temperature is approximately 15 million degrees Celsius. The density is about 150 times that of water, denser than any solid on Earth, yet still a gas because the temperature is so high that atoms are completely ionized into a plasma of free nuclei and electrons. The pressure is immense, billions of times atmospheric pressure, the weight of the overlying layers compressing the core. In this extreme environment, protons move at enormous speeds, thousands of kilometers per second, colliding constantly. Most collisions result in nothing but a bounce, electromagnetic repulsion preventing fusion. But occasionally, very occasionally, quantum tunneling allows fusion. A proton converts to a neutron, a deuterium nucleus forms. A neutrino is released. That neutrino, being nearly massless and interacting only weakly with matter, escapes the Sun almost immediately, passing through the overlying layers as if they weren't there, streaming out into space at the speed of light. Some of those neutrinos pass through Earth and through you. Every second, ghostly particles from the Sun's core, barely interacting, providing direct evidence of fusion happening 93 million miles away. The energy released in fusion takes a different path. It's initially in the form of gamma rays, high-energy photons, and the kinetic energy of the reaction products. These photons don't escape directly. Instead, they're absorbed by nearby particles and re-emitted in random directions, absorbed again, re-emitted, bouncing around in an endless random walk. The process is called radiative diffusion, and it's extraordinarily slow. A photon created in the Sun's core will take, on average, 100,000 years to reach the surface. 100,000 years of bouncing around inside the Sun, absorbed and re-emitted countless trillions of times, gradually working its way outward. The photon you see when you look at the Sun today was created in the core 100,000 years ago, during the late Pleistocene, when humans were still hunter-gatherers, when mammoths still roamed the Earth. The journey changes the photon. It starts as a gamma ray, but each absorption and re-emission can lower its energy. By the time it finally emerges from the Sun's photosphere, the visible surface, it's much more likely to be a visible light photon or an infrared photon, the original gamma ray's energy divided among many lower energy photons through the countless interactions during its 100,000-year journey. Inside the Sun, structure and layers. You now peer inside the Sun with modern understanding, seeing it not as a uniform glowing sphere, but as a complex structure of layers, each with distinct properties and roles. The core, as described, is where fusion occurs. It extends from the centre out to about 25% of the solar radius. This is the only region hot and dense enough for fusion. Beyond the core, no fusion occurs. The outer layers are supported by the pressure of radiation and hot gas, but they're not hot enough to fuse hydrogen. Surrounding the core is the radiative zone, extending from 25% to about 70% of the solar radius. Here, energy transport is through radiation, photons bouncing around in that slow, random walk. The material is hot enough and dense enough that photons can't travel far before being absorbed, so radiative diffusion is the dominant process. The temperature decreases gradually with distance from the core, 7 million degrees at the top of the radiative zone, compared to 15 million in the core. Then comes the convective zone, from 70% of the radius up to the surface. Here, temperature and density have decreased to the point where radiative diffusion is no longer efficient. Instead, energy is transported by convection. Hot plasma rises, cools as it approaches the surface, releases its energy, then sinks back down to be reheated, creating vast circulation patterns. Imagine the Sun's convective zone like boiling water in a pot, though the scale is vastly different. You can see the evidence of convection directly on the Sun's surface. Through a properly filtered telescope showing the photosphere in high resolution, the surface appears granulated, covered with bright cells separated by darker boundaries. Each granulation cell is a convection cell, with hot plasma rising in the bright centre and cooler plasma sinking at the darker edges. The cells are enormous, typically about 1,000 kilometres across, roughly the size of Texas, and they evolve on timescales of minutes, hot material rising, cooling, sinking in an endless churning motion. Watch the granulation pattern for an hour and you'll see it constantly changing. Cells appearing, growing, merging with neighbours, splitting apart, the surface in constant motion like time-lapse footage of boiling porridge. Though the scale is planetary and the substance is ionized gas at thousands of degrees. The motion reveals the tremendous energy being transported from the interior. Heat generated in the core hundreds of thousands of years ago, finally emerging through this last layer of convection before radiating into space. Larger convection patterns also exist, though they're harder to observe. Supergranulation cells, roughly 30,000 kilometres across, form a larger scale circulation pattern beneath the granulation, and below that possibly even larger cells called giant cells that span significant fractions of the solar radius. These nested scales of convection, from granulation to supergranulation to giant cells, create a complex three-dimensional churning throughout the outer 30% of the Sun's interior, mixing material, transporting heat, generating magnetic fields through dynamo action. The photosphere itself, the visible surface, is actually not a solid surface at all. It's simply the layer where the Sun's gas becomes opaque, where photons can finally escape into space rather than being immediately reabsorbed. It's about 500 kilometres thick, thin compared to the Sun's 700,000 kilometre radius, and it's what we see when we look at the Sun. The temperature is about 5,500 degrees Celsius, much cooler than the core, but still hot enough to glow white hot. Above the photosphere lies the chromosphere, a thin, irregular layer a few thousand kilometres thick. It's normally invisible, overwhelmed by the bright photosphere, but during total solar eclipses, when the photosphere is blocked, the chromosphere appears as a reddish glow around the Moon's dark disk. The reddish colour comes from hydrogen emission, particularly the H-alpha line. The chromosphere is actually hotter than the photosphere. Temperatures rise from 5,500 degrees at the bottom to 20,000 degrees at the top, which seems to violate thermodynamics until you realise energy is being deposited from below by sound waves and magnetic processes, not by radiative heating. And beyond the chromosphere is the corona, the Sun's outer atmosphere, visible during total eclipses as a pearly white glow with delicate streamers extending millions of kilometres into space. The corona is extraordinarily hot, 1 to 3 million degrees, sometimes even hotter during active periods. Why the corona is so hot when it's so far from the fusion core is one of solar physics' great puzzles. The answer involves magnetic fields and plasma physics. Tangled magnetic field lines release energy through reconnection, heating the coronal plasma to these extreme temperatures. The solar wind streams outward from the corona, a constant flow of charged particles, mostly protons and electrons, escaping the Sun's gravity and flowing through interplanetary space at speeds of 300 to 800 kilometers per second. The solar wind creates a bubble around the solar system called the heliosphere, extending far beyond Pluto, only ending where it meets the interstellar medium at the heliopause, more than 100 times Earth's distance from the Sun. Solar cycles and activity, the rhythm of magnetic storms. Imagine you're watching the Sun change over years and decades. You're with Heinrich Schwabe, a German apothecary and amateur astronomer, who in 1826 begins a project that will consume the next 2 decades of his life: daily observation and sketching of sunspots. His original goal was to discover an intramercurial planet by watching for transits across the Sun's face, but he became fascinated by the sunspots themselves. The routine is demanding. Every clear day, weather permitting, Schwabe projects the Sun's image onto paper and carefully draws the sunspots visible that day, noting their positions and sizes. Year after year, the observations accumulate. Some days there are many spots. Other days there are few or none. The spots appear, evolve, rotate across the visible disk as the Sun turns, and disappear either by rotating around to the far side or by simply fading away. The work requires dedication bordering on obsession. Schwabe runs an apothecary shop in Dessau, Germany, conducting his astronomical observations in whatever spare time his business allows. Early morning observations before the shop opens, afternoon observations during lunch breaks. The work is solitary. Few people understand why he's doing it, why he spends hours staring at projected solar images, making careful drawings. But he persists. The observations must be made at the same time each day when possible, to see the same longitude of the Sun and track individual spots across successive days. Each drawing is carefully filed with the date, time, and any notes about spot characteristics. Some spots are small, barely visible dots. Others are large enough to swallow Earth several times over, complex structures with dark central umbrae surrounded by lighter penumbrae. Structures that evolve from day to day as magnetic fields twist and reorganize beneath the photosphere. Schwabe learns to recognize spots' life cycles. New spots appear suddenly, often in groups. They grow over days, reaching maximum size, then gradually shrink and fade over weeks. The largest spots can persist for months, rotating across the visible disk, disappearing around the limb, reappearing 13 days later on the opposite limb after making the journey around the Sun's far side. Following these long-lived spots across multiple rotations, Schwabe determines the Sun's rotation period, approximately 27 days as seen from Earth, though closer to 25 days accounting for Earth's motion around the Sun. After 17 years of daily observations, 17 years of patient work, thousands of observations logged, Schwabe notices a pattern. The number of sunspots visible is not random. It varies in a cycle, taking about 10 years to go from many spots, solar maximum, to few spots, solar minimum, and back to maximum again. The cycle is irregular. Sometimes it's as short as 9 years, sometimes as long as 13, but the average is close to 11 years. The discovery is announced in 1843, but initially it attracts little attention. It's only when Rudolf Wolf in Switzerland begins systematic sunspot observations and confirms and extends Schwabe's work that the scientific community takes notice. Wolf develops the Wolf sunspot number, a formula that counts both individual spots and groups of spots to create a single daily index of solar activity. Using historical records, Wolf extends the sunspot cycle back to 1755, identifying multiple cycles and confirming their approximate 11-year rhythm. But the sunspot cycle is more complex than just a variation in spot count. Richard Carrington, a British astronomer, discovers in 1858 that sunspots don't appear randomly over the solar surface. They appear in 2 latitude bands, one in each hemisphere, roughly 30 to 40 degrees north and south of the equator at the start of each cycle. As the cycle progresses, new spots appear at progressively lower latitudes, moving toward the equator. By solar minimum, spots appear near 5 to 10 degrees latitude. Then the pattern resets with spots appearing again at high latitudes as a new cycle begins. The pattern, when plotted as latitude versus time, creates what's called the butterfly diagram, because the shape resembles butterfly wings. The pattern has continued reliably for as long as sunspots have been observed systematically. Each 11-year cycle follows the same latitude progression, the spots marching from mid-latitudes toward the equator as the cycle evolves. But what causes the cycle? The answer involves the Sun's magnetic field, though this won't be understood until the 20th century, when George Ellery Hale discovers in 1908 that sunspots are regions of intense magnetic field. Using spectroscopy and the Zeeman effect, the splitting of spectral lines in the presence of a magnetic field, Hale measures field strengths in sunspots of thousands of Gauss, far stronger than Earth's magnetic field. Sunspots, it turns out, are cooler and darker than the surrounding photosphere because the magnetic field suppresses convection, reducing heat transport from below. They appear in pairs because they're where magnetic field lines emerge from below the surface at one spot and re-enter at another. And here's a key insight. Hale discovers that the leading and following spots in each pair have opposite magnetic polarity, and this polarity pattern reverses between hemispheres and between successive cycles. What this means, the solar cycle is actually 22 years, not 11. After 11 years, the spot count returns to maximum, but the magnetic polarity has flipped. After another 11 years, the polarity returns to its original configuration. The Sun's magnetic field completely reverses every 11 years, then reverses back 11 years later. The mechanism driving this is the solar dynamo, the combination of the Sun's rotation and convection generating and amplifying magnetic fields through complex magneto-hydrodynamic processes. Differential rotation, the equator rotating faster than the poles, winds up magnetic field lines, strengthening them. Convection creates new field lines and brings them to the surface. The field becomes progressively more tangled until it breaks down and reorganizes. Then the cycle begins again. You stand now in the modern routine of solar observation. Solar observatories operate continuously, monitoring the Sun daily. Telescopes equipped with special filters observe sunspots, track their evolution, measure their magnetic fields. The observations are compiled into indices: sunspot number, solar flux measurements, active region counts, each tracked daily and published for researchers and space weather forecasters. Modern solar observatories are highly automated but still require human oversight. Imagine visiting one, perhaps the National Solar Observatory in New Mexico or the Solar Dynamics Observatory Mission Control. The telescopes track the Sun automatically, compensated for Earth's rotation, capturing images every few seconds in multiple wavelengths. Computers process the data in real time, identifying and numbering active regions, measuring magnetic field strengths, detecting flares and prominences. But humans still review the data, watching for anomalies, making judgment calls about whether an active region is likely to produce a major flare, whether a coronal mass ejection is Earth-directed and warrants a warning. The work has the feel of meteorology combined with air traffic control, monitoring multiple data streams, watching for signs of developing activity, issuing forecasts and warnings when conditions warrant. The smell in a modern observatory is mostly of electronics and air conditioning, very different from the brass and oil smell of classical observatories. The sounds are the quiet hum of computers, the click of keyboards, occasional conversation between observers discussing a particularly interesting active region. The displays show the Sun in wavelengths invisible to human eyes. Ultraviolet images showing the chromosphere, X-ray images showing the hot corona, magnetograms showing field strengths in false colour. Through these instruments, solar physicists watch the sun's magnetic field twist and tangle, watch filaments of cool plasma suspended in magnetic loops above the surface, watch the occasional sudden reorganization of field lines that releases stored magnetic energy in a flare, watch coronal mass ejections explosively hurling billions of tons of plasma into space. The sun, which appears so constant and unchanging to casual observation, reveals itself as dynamic, turbulent, constantly active when observed with proper instruments. The data show that solar activity affects Earth. During solar maximum, when sunspots are numerous, solar flares and coronal mass ejections are more frequent. These events can disrupt Earth's magnetic field, causing geomagnetic storms that create auroras, but also disrupt satellites, radio communications, even power grids. During solar minimum, the sun is quieter, but not completely inactive. Events still occur, just less frequently. The most famous solar event in recorded history occurred during Cycle 10 in 1859. On September 1st, Richard Carrington was doing his routine solar observation when he witnessed something extraordinary. A bright flash on the sun's surface, a solar flare visible in white light through his telescope. Within hours, auroras appeared worldwide, even in tropical latitudes. Telegraph systems went haywire, some operators receiving shocks, some telegraph stations burning. The event, known as the Carrington event, is estimated to have been the most powerful geomagnetic storm in recorded history. Carrington himself was stunned by what he'd seen. He was projecting the sun's image onto a screen in his private observatory, carefully sketching a complex sunspot group, when two brilliant white patches suddenly appeared within the sunspot group, intensifying rapidly, lasting about 5 minutes before fading. He rushed to find someone else to witness it, but by the time he returned with another observer, the brightening had already peaked and was diminishing. He knew immediately this was something unusual, something possibly unprecedented. Solar flares bright enough to see in white light are exceptionally rare. Most flares are visible only in hydrogen alpha or other specific wavelengths. That night, the auroras began. Normally confined to high latitudes, aurora borealis and aurora australis were visible worldwide. People in Cuba, the Caribbean, Rome, even near the equator saw auroral displays. The lights were brilliant enough to read by at night. Newspaper accounts describe people waking in the middle of the night thinking it was dawn because the aurora light was so bright. Miners in the Rocky Mountains reportedly woke and began preparing breakfast, thinking morning had come. The telegraph networks, the cutting edge of Victorian communication technology, went into chaos. Telegraph operators reported sparks leaping from equipment, shocks received when touching the metal components, some operators knocked unconscious. Some telegraph lines continued operating even with their batteries disconnected, powered by the electrical currents induced in the long wires by the geomagnetic storm. Telegraph paper caught fire in some stations from the electrical surges. The disruption lasted for days as operators tried to work around the interference, sending messages in fits and starts during brief, calmer periods. If a Carrington-level event occurred today, it could be catastrophic for modern technological infrastructure. Satellite damage, GPS disruption, radio blackouts, power grid failures potentially lasting weeks or months in affected regions. Solar physicists and space weather forecasters monitor the sun constantly, watching for signs of major eruptions that might threaten Earth, trying to provide warning to satellite operators and power companies to take protective measures. The daily routine of solar monitoring has become increasingly sophisticated. Space-based telescopes observing in UV and X-ray wavelengths that don't penetrate Earth's atmosphere, instruments measuring the solar wind, coronagraphs blocking the bright photosphere to watch the faint corona, magnetographs mapping the sun's magnetic field in detail. The sun is watched more carefully now than at any point in human history. The ancient object of worship now subject to continuous scientific scrutiny, its moods and cycles tracked in real time. Remember those ancient priests marking sunrise positions at Stonehenge? Now satellites measure the sun's output to 8 decimal places, tracking the 0.1% variation over the solar cycle, correlating it with Earth's climate subtly. The journey from worship to measurement is complete, though the fundamental relationship remains. Humanity depending on the sun, watching it, trying to understand and predict its behaviour, knowing that despite all our technology, we remain utterly dependent on the steady shining of this ordinary star. The circuits in your mind are quieting now as sleep approaches. The sun continues its fusion, 4 million tons of mass converting to energy every second, hydrogen becoming helium in the endless nuclear furnace at its core, photons beginning their 100,000-year journey to the surface, the solar dynamo winding and unwinding magnetic fields in its 11-year rhythm, the steady processes that have continued for 4.5 billion years and will continue for 5 billion more. Rest now, while the sun shines on, tireless and essential, the ancient mystery revealed but no less wondrous for being understood. You now stand in modern times, though what counts as modern keeps shifting forward. It's the space age, beginning with the first satellites in the late 1950s, accelerating through the 1960s and 70s, continuing to the present day. For the first time in history, humans can observe the sun from above Earth's atmosphere, seeing wavelengths that never reach the ground, watching our star with clarity impossible from the surface. Imagine you're at the launch of Skylab, America's first space station, in 1973. The facility includes the Apollo Telescope Mount, the most sophisticated solar observatory ever flown at that time. You can hear the countdown, feel the ground shaking as the Saturn V rocket lifts off, watch the brilliant exhaust plume as the massive vehicle climbs into the sky, carrying with it instruments that will revolutionize solar physics. The astronauts aboard Skylab spend hundreds of hours observing the sun across multiple missions. They photograph it in ultraviolet wavelengths that Earth's atmosphere blocks completely, revealing the chromosphere and corona in unprecedented detail. They capture images of solar flares erupting, vast prominences arcing above the surface, coronal holes where the magnetic field opens up, and fast solar wind streams outward. The observations are stunning, revealing a sun far more dynamic and complex than ground-based observations ever suggested. The routine aboard Skylab includes daily solar observation sessions, powering up the telescope mount, selecting wavelengths and filters, tracking the sun as the station orbits Earth every 90 minutes, photographing active regions and capturing spectroscopic data, changing film magazines when they're exhausted, carefully logging every observation. The work is demanding, conducted in the cramped confines of the space station, but the results are extraordinary. After Skylab comes a succession of solar space missions. The Solar Maximum mission, launched in 1980, focuses on solar flares and coronal mass ejections during a solar maximum. The Yoko satellite, Japanese-led with international participation, observes the sun in X-rays throughout the 1990s. Each mission adds layers to understanding, each reveals phenomena invisible from the ground or even from previous space missions. Then comes SOHO, the Solar and Heliospheric Observatory, a joint NASA-ESA mission launched in 1995 and still operating decades later, one of the most successful scientific satellites ever flown. SOHO orbits not around Earth but around a point between Earth and Sun called L1, a gravitationally stable location where it can observe the Sun continuously without Earth ever blocking the view. You find yourself in a mission control room watching SOHO data arrive in real time. The screens show the Sun in multiple wavelengths simultaneously. Ultraviolet images revealing the turbulent chromosphere, extreme ultraviolet showing coronal loops and active regions, coronagraph images blocking the bright photosphere to reveal the faint corona and any coronal mass ejections erupting outward. The data streams continuously, 24 hours a day, building up a decades-long record of solar activity with no gaps, no interruptions for weather or daylight. SOHO has revolutionized several areas of solar physics. Its coronagraphs have detected thousands of coronal mass ejections, allowing scientists to study their properties statistically, to understand what triggers them, to improve predictions of when they'll hit Earth. Its helioseismology instruments measure oscillations in the Sun's surface caused by sound waves reverberating through the interior, allowing scientists to map the Sun's internal structure and rotation like seismologists map Earth's interior using earthquake waves. The helioseismology is particularly elegant. The Sun rings like a bell, or rather like millions of bells, with countless oscillation modes, each corresponding to sound waves travelling through different paths in the interior. By measuring the frequencies of these oscillations, detected as slight Doppler shifts in spectral lines across the solar surface, and comparing them to theoretical models, scientists determine the Sun's internal temperature profile, density, structure, rotation rate at different depths, even the abundance of helium in regions too deep for direct observation. It's a remarkable technique, using sound waves to see inside the Sun. More recent missions continue advancing solar physics. The Solar Dynamics Observatory, launched in 2010, captures images of the Sun every 0.75 seconds in multiple wavelengths, producing data at a rate exceeding all other NASA science missions combined. The resolution is extraordinary. You can see individual granulation cells, track their evolution minute by minute, watch the constant churning of the photosphere in mesmerizing detail. The SDO images have become iconic, appearing in documentaries and educational materials worldwide. The Sun in extreme ultraviolet looks alien, nothing like the simple yellow disk visible to our eyes. Different wavelengths reveal different temperature regimes, cool filaments of plasma suspended in magnetic loops, hot active regions glowing intensely, the corona's complex structure that changes hour by hour. Time-lapse sequences show the Sun as a dynamic, turbulent plasma ball, magnetic fields twisting and reorganizing, prominence eruptions arcing hundreds of thousands of kilometers above the surface, coronal holes appearing and evolving as the magnetic field opens up. The data volume is staggering. SDO transmits about 1.5 terabytes per day, more data in a single day than many earlier solar missions collected in their entire lifetimes. Processing this requires powerful computers, sophisticated algorithms, and teams of scientists working to extract meaning from the flood of information. But the result is unprecedented. A continuous high-resolution record of solar activity, watching the Sun evolve through a complete solar cycle with no gaps, capturing every significant event, building a comprehensive understanding of how the Sun behaves. And most recently, the Parker Solar Probe, launched in 2018, is diving directly into the Sun's corona, closer than any spacecraft has ever ventured. It approaches to within 4 million miles of the Sun's surface, about 4% of Earth's distance, enduring temperatures exceeding 1000 degrees Celsius behind its heat shield, measuring the solar wind at its source, sampling the corona directly. The mission is revealing how the corona is heated, how the solar wind is accelerated, answering questions that have puzzled solar physicists for decades. You stand now in the routine of modern space-based solar observation. Multiple satellites monitor the sun simultaneously, their data integrated into comprehensive models. Solar physicists review daily reports, active region development, flare occurrence, coronal mass ejection detections, solar wind speed and density, magnetic field measurements. The sun is watched more carefully than any previous generation could imagine, its behaviour tracked in real time, its effects on Earth's space environment monitored constantly. The smell in mission control rooms is of coffee and electronics, the sound of quiet conversation and keyboard clicking, the visual environment dominated by screens showing the sun's activity from multiple perspectives. There's a quality almost like air traffic control or weather forecasting, monitoring developing situations, issuing alerts when necessary, the constant awareness that the sun's activity has real consequences for satellites, astronauts, power grids, GPS systems, all the technological infrastructure modern civilization depends on, solar weather and its effects on Earth. Imagine you're experiencing a major solar storm, though you probably won't notice directly. It's March 13th, 1989. 3 days earlier, a massive coronal mass ejection erupted from an active region on the sun's surface. 1 billion tons of plasma hurled into space at millions of miles per hour, carrying with it twisted magnetic fields that break free from the sun's atmosphere. The ejection travels through space, gradually expanding, gradually slowing, but still moving at hundreds of kilometers per second when it reaches Earth. You're asleep when it arrives. The first sign is at ground-based magnetometers. Sudden irregular fluctuations in Earth's magnetic field as the shock wave compresses the magnetosphere. Then the main body of the CME arrives and Earth's magnetic field begins a period of wild turbulence that will last for hours. In the Arctic and in high southern latitudes, auroras blaze across the sky. But these aren't the usual greenish curtains. These are vivid reds and purples, auroras so bright and extensive that they're visible as far south as Texas and Florida, as far north from the South Pole as Queensland, Australia. People who've never seen an aurora in their lives stand in their yards watching the sky dance with coloured light, posting on early internet forums, asking what's happening. Is this dangerous? Is the world ending? The auroras are beautiful, but they're just a visible symptom. The real action is happening in the upper atmosphere, where charged particles from the CME, channeled by Earth's magnetic field, collide with atmospheric molecules, exciting them to higher energy states. When they relax back down, they emit light. Oxygen producing green and red, depending on altitude, nitrogen producing blues and purples. But the particles also deposit energy, heating the upper atmosphere, causing it to expand upward. Satellites in low Earth orbit experience increased drag, their orbits decaying faster than predicted, requiring adjustments to avoid premature re-entry. In power grids across North America, induced electrical currents surge through transmission lines. The changing magnetic field from the geomagnetic storm creates electric fields in the conductive ground, and these fields drive currents through grounded systems like power grids. The currents can saturate transformers, overheat them, damage them. In Quebec, the entire provincial power grid collapses, plunging millions into darkness for 9 hours on a cold March night. The blackout isn't from damage to generation facilities or transmission lines themselves, but from transformer failures and protective systems triggering to prevent further damage. Satellites experience glitches. Energetic particles penetrate electronic components, causing bit flips in computer memory, false commands, temporary malfunctions. Most satellites are designed to tolerate this, with error-correcting codes and redundant systems, but occasionally damage is permanent. Communication systems are disrupted. High-frequency radio, which normally bounces off the ionosphere to provide long-distance communication, becomes unreliable as the ionosphere's properties change dramatically during the storm. Airlines reroute polar flights because radio communication at high latitudes is degraded and radiation exposure increases. GPS systems show position errors larger than usual. GPS relies on precisely timed signals from satellites, and ionospheric disturbances affect how those signals propagate, introducing errors. Modern GPS receivers can compensate partially, but during severe storms, errors can reach tens of meters or more. For precision applications, surveying, precision agriculture, scientific measurements, the degraded accuracy can be problematic. The storm lasts for days in its effects, though the most intense period is just hours. Gradually, the magnetosphere relaxes back toward normal. The induced currents in power grids subside. The ionosphere recovers. The auroras retreat to their usual high latitudes. Power is restored in Quebec, but the storm has demonstrated that space weather is real, that events on the Sun 93 million miles away can have tangible effects on Earth, that our technological infrastructure is vulnerable in ways our ancestors never experienced because they didn't have the technology to be affected. You stand now in a space weather forecasting centre, perhaps NOAA's Space Weather Prediction Centre in Boulder, Colorado. The work resembles terrestrial weather forecasting, but the data sources are different. Solar observations from multiple satellites, solar wind measurements from spacecraft positioned between Earth and Sun, magnetometer networks across the globe, ionospheric monitoring stations. Forecasters watch for signs of eruptions on the Sun, track coronal mass ejections as they propagate through space, predict when they'll arrive at Earth and how severe their effects might be. A typical forecast might say, active region 12,673 poses a continued threat for strong flares. A coronal mass ejection erupted at 14:30 UTC on September 6th, currently propagating earthward, estimated arrival September 8th, 1200 UTC, plus or minus 6 hours. G3, strong. Geomagnetic storm conditions expected. Power system operators should be alert for possible grid irregularities. Satellite operators should place spacecraft in safe modes if necessary. The forecasts are probabilistic. Predicting exactly when a specific active region will produce a flare is still beyond current capabilities. We can say an active region looks magnetically unstable, but the exact trigger moment remains unpredictable. Predicting CME arrival times is challenging because we don't measure the CME's speed with perfect accuracy, and it can accelerate or decelerate as it moves through the solar wind. But the forecasts have improved dramatically over decades, and they provide actionable information to industries and agencies that need it. Earth's magnetic field is what protects us from the worst of solar activity. The magnetosphere, generated by electric currents in Earth's liquid iron outer core, extends tens of thousands of kilometers into space, deflecting the solar wind around Earth like water flowing around a rock in a stream. Without this magnetic shield, the solar wind would strip away Earth's atmosphere over geological time, as happened to Mars after its magnetic field died. The magnetosphere channels charged particles toward the poles, which is why auroras occur at high latitudes rather than everywhere. But the magnetosphere is not perfectly protective. During major geomagnetic storms, it compresses dramatically on the sunward side and stretches out on the night side. The boundary, where Earth's field meets the solar wind, can move inward to just above geostationary satellite altitude, about 36,000 kilometers up, instead of its usual 60,000 kilometers or more. Particles can penetrate deeper into the inner magnetosphere, reaching regions where expensive satellites orbit, increasing radiation exposure beyond design tolerances. Astronauts aboard the International Space Station receive warnings during major solar events. They might retreat to more shielded areas of the station during solar proton events, which can deliver significant radiation doses to crew in just hours. They might postpone spacewalks if a proton event is forecast or underway. The radiation exposure from space weather is one limiting factor for long-duration missions beyond low Earth orbit, something that must be addressed for crewed missions to Mars, where travellers would spend months in interplanetary space without Earth's magnetosphere for protection. Remember those ancient peoples who feared the sun might not return. Modern civilization fears the opposite problem, that the sun might be too active, that a truly major storm like the Carrington event could damage infrastructure that society depends on, causing cascading failures in power grids, satellites, communications. There are plans, preparations, but also uncertainties. How severe could the worst solar storm be? How resilient is our infrastructure? How quickly could we recover? These questions drive continued solar monitoring and research. The sun's life cycle and eventual transition time stretches forward now into the deep future, though future is the wrong word because these events haven't happened yet. But physics is predictive. We can calculate the sun's evolution with confidence because we've observed thousands of stars at different evolutionary stages, because we understand nuclear fusion and stellar structure, because the laws of physics are reliable even when extrapolated millions and billions of years forward. The sun formed approximately 4.6 billion years ago from a collapsing cloud of gas and dust. The cloud was mostly hydrogen and helium left over from the Big Bang, with traces of heavier elements forged in previous generations of stars that had lived, died, and scattered their enriched ashes into space. As the cloud collapsed under its own gravity, it spun faster, flattened into a disk, heated up at the centre. When the core temperature reached about 10 million degrees, hydrogen fusion ignited, the sun began shining, the collapse halted, a star was born. For the past 4.6 billion years, the sun has been in the main sequence phase, the long stable period of hydrogen burning that stars spend most of their lives in. It's been remarkably constant, with luminosity varying by less than a fraction of a percent, though there has been a slow, gradual brightening. The sun today is about 30% more luminous than when it first formed. This happens because helium ash from fusion accumulates in the core, increasing the mean molecular weight, requiring higher core temperatures to maintain pressure support, which increases the fusion rate, which increases luminosity. But the change is slow, imperceptible on human timescales. The sun will continue in main sequence for approximately another 5 billion years. 5 billion years is an almost incomprehensible time. Complex, multicellular life has existed on Earth for less than 1 billion years. Humans have existed for a few 100,000 years. 5 billion years is longer than Earth's entire history to date. Whatever descendants of humanity exist then, if any, will be as different from us as we are from bacteria. But eventually, inevitably, the hydrogen in the sun's core will be exhausted. The core will be pure helium, fusion ash that can't fuse further under current conditions. Fusion will continue in a shell surrounding the inert helium core, burning the remaining hydrogen there. The core, no longer supported by fusion pressure, will begin to contract under gravity, heating up as it does. The contracting core will release gravitational energy, which will heat the overlying layers. Paradoxically, even as the core contracts, the outer layers will expand dramatically. The Sun will grow into a red giant, its outer atmosphere swelling to perhaps 100 times its current size. The photosphere will cool as it expands. That's why it's called red giant, because cooler photospheres emit more red light than hot ones. But the total luminosity will increase because the surface area will be so much larger. This red giant phase will last perhaps 1 billion years. During this time, the Sun will engulf the inner planets. Mercury will definitely be consumed. Venus probably will be. Earth is on the edge. Different models give different predictions depending on exact assumptions about mass loss and orbital evolution. But even if Earth isn't technically engulfed, the increased solar luminosity will boil away the oceans, strip away the atmosphere, sterilize the surface completely. Earth will become uninhabitable long before the Sun actually reaches it. Eventually, the contracting helium core will reach approximately 100 million degrees, hot enough for helium fusion to begin. 3 helium nuclei fuse to make carbon in a process called the triple alpha reaction. The helium ignition is sudden, a helium flash that releases enormous energy over a few seconds, though the outer layers are so thick that the flash isn't visible from outside. The Sun will settle into a new equilibrium, burning helium in the core and hydrogen in a shell, somewhat smaller and less luminous than the largest red giant phase. After the helium is exhausted, the Sun will undergo another expansion, shedding its outer layers in a planetary nebula, though planetary is a misleading name. These have nothing to do with planets, but are shells of glowing gas surrounding dying stars. The ejected material will expand into space, eventually dissipating, mixing with the interstellar medium available for formation of future stars and planets. The Sun's contribution to the cosmic recycling system. What remains will be the core, a white dwarf, Earth-sized, but enormously dense, about 1 million times denser than water. The white dwarf will be hot initially, with a surface temperature of perhaps 100,000 degrees, but it will have no internal energy source. It will shine purely by radiating away its stored thermal energy, gradually cooling, fading through white to yellow to red, to eventually a black dwarf, though the universe isn't old enough yet for any black dwarfs to exist. Even the oldest white dwarfs are still faintly warm. The white dwarf Sun will cool for trillions of years, far longer than the current age of the universe. It will eventually reach equilibrium with the cosmic microwave background radiation about 3 degrees above absolute zero, and then cool no further unless the universe itself cools. This is the Sun's ultimate fate, a dark, cold cinder, the remnant core of a once bright star, drifting through space for timescales that dwarf all of history and recorded time combined. This is said calmly without alarm, because it's so far in the future. 5 billion years. Civilization need not worry about the Sun's transition. If humanity survives at all for even 1 million years, a mere 0.02% of the remaining main sequence lifetime, we'll be so advanced, so transformed, so fundamentally different that the Sun's eventual evolution will be anticipated, prepared for, perhaps even manipulated if that's physically possible, or simply left behind as we migrate to younger stars. Stellar evolution is now understood with confidence through observations and computer models. Astronomers observe stars of different masses at different evolutionary stages, seeing main sequence stars like the Sun, red giants, planetary nebulae, white dwarfs, the full sequence. Computer models start with a star's initial mass and composition, calculate how fusion proceeds, how structure changes, how luminosity and temperature evolve over time. The models match observations remarkably well. The Sun's future is as certain as physics can make predictions, written in the present behaviour of 1 million similar stars scattered through the galaxy. There's something oddly calming about this knowledge. The Sun has been here for 4.6 billion years. It will be here for another 5 billion. On human timescales, it's eternal. The constancy that ancient peoples observed and worshipped is real. The Sun doesn't change, not on the timescales of empires or species, or even continents. It simply shines, day after day, year after year, millennium after millennium, eon after eon, steadily fusing hydrogen to helium, steadily radiating energy into space, steadily making life possible on at least one small planet. Solar energy and humanity's relationship with the Sun. You reflect now on how civilization depends on the Sun, though the dependence is often invisible. Every calorie of food begins with photosynthesis, plants capturing sunlight, using its energy to convert carbon dioxide and water into sugars, building the base of the food chain that supports all animal life. The meat you eat comes from animals that ate plants. The plants grew using sunlight. Solar energy captured by chlorophyll, converted to chemical energy, passed up the food chain. We are literally made of sunlight, transformed through biological processes into flesh and bone. Fossil fuels are ancient sunlight. Coal is compressed plant matter from swamps and forests 300 million years ago. Oil and natural gas are altered remains of ancient marine organisms. The energy stored in these fuels originally came from the Sun, captured by photosynthesis millions of years ago, buried, compressed, transformed chemically into concentrated energy sources. When we burn fossil fuels, we're releasing that ancient solar energy, using up in centuries what took millions of years to accumulate. Wind energy is solar energy. The Sun heats Earth's surface unevenly, creating temperature differences that drive atmospheric circulation, creating wind. Wind turbines capture that solar-powered airflow and convert it to electricity. Hydroelectric power is solar energy. The Sun evaporates water from oceans, the water vapour rises, forms clouds, falls as rain or snow in mountains, flows downhill through rivers and dams where its gravitational potential energy, originally provided by solar-powered evaporation, is converted to electricity. Wave energy is solar energy stirring the ocean's surface through wind. Wave energy, even tidal energy, has a solar component, though the Moon's gravity is the primary driver. Nearly every energy source humans use traces back to the Sun. The main exceptions are nuclear fission, using uranium and thorium created in ancient supernovae before the solar system formed, and geothermal energy, using Earth's internal heat from radioactive decay and residual formation heat. And now, increasingly, we're using solar energy directly. Solar panels, photovoltaic cells, convert sunlight to electricity without the intermediary of photosynthesis, or fossil fuels, or wind, or evaporation. The technology has existed since the 1950s, but has become practical and economical only in recent decades as efficiency improved and manufacturing costs fell. You stand now in a solar farm, perhaps in the Mojave Desert, or in Spain or in China. The landscape is transformed, thousands of solar panels arranged in neat rows, each angled to catch maximum sunlight, each converting photons to electrons through the photoelectric effect. The panels are dark blue or black, slightly warm to the touch, even though they're converting a substantial fraction of incident light to electricity rather than heat. The smell is of dust and sun-baked ground and the faint electrical scent of high-voltage equipment at the collection points. The sound is mostly silence. No moving parts in solar panels, just the occasional click of tracking motors adjusting panel angles to follow the sun, the hum of inverters converting DC from the panels to AC for the grid, the wind moving across the desert. The scale is impressive. A large solar farm might cover several square miles, generating hundreds of megawatts, enough for tens of thousands of homes. Solar energy is now the cheapest form of electricity in many locations, cheaper than coal or gas or nuclear. This is recent. As recently as the 1990s, solar was niche, expensive, suitable only for remote locations without grid access. But costs have fallen exponentially, driven by manufacturing improvements, economics of scale, technological refinements. The trajectory continues. Solar will likely become the dominant source of new electricity generation globally, not because of environmental concerns primarily, but because it's economically optimal. The intermittency remains a challenge. Solar panels generate electricity only when the sun shines, nothing at night, less on cloudy days. But energy storage is improving, batteries becoming cheaper and more capable, allowing solar energy captured during the day to be used at night. Grid integration strategies help, balancing solar with other sources using geographic diversity where the sun is shining somewhere, improving transmission to move power where it's needed. And there's a larger dream: fusion power. If the sun generates energy by fusing hydrogen to helium, why can't we do the same on Earth? The physics is straightforward. The engineering is extraordinarily difficult. Fusion requires temperatures of millions of degrees, pressures of billions of atmospheres, confinement for long enough that fusion occurs at a net positive energy rate. The sun achieves this through sheer mass. The gravitational pressure at the core is enormous. The confinement time is essentially infinite. On Earth, we don't have stellar mass quantities of hydrogen to compress gravitationally. Instead, engineers use magnetic confinement in tokamaks, toroidal magnetic chambers that contain hot plasma in a magnetic bottle, or inertial confinement using powerful lasers to compress tiny fuel pellets to fusion conditions for brief instants. The experiments work. Fusion occurs, energy is released. But getting more energy out than you put in, sustaining the reaction, engineering a practical power plant, these remain challenges. You stand in a fusion research facility, perhaps ITER in France, an international project attempting to demonstrate net energy gain from magnetic fusion. The tokamak is enormous, a complex machine of superconducting magnets cooled to near absolute zero, vacuum chambers where plasma at 100 million degrees will be confined just meters away from those cryogenic magnets. Diagnostic systems to measure every parameter of the plasma, heating systems to get it hot enough for fusion. The smell is of liquid helium coolant, of the particular scent of high-tech laboratories with careful climate control. The sound is of vacuum pumps, of liquid nitrogen and liquid helium systems maintaining the superconducting magnets, of the quiet hum of control systems. The visual is of a massive complex machine, gleaming metal and vacuum chambers, cables everywhere, the scale impressive and slightly intimidating. Fusion power remains decades away despite decades of research. Each generation of experiments teaches more, gets closer, but practical fusion power plants are always 20 years away in the running joke of the field. But the prize is enormous, nearly limitless energy from deuterium extracted from seawater and lithium from mines, no carbon emissions, no long-lived radioactive waste. The same power source that makes the sun shine, replicated on Earth. Whether fusion power arrives in 20 years or 50 or never, solar energy, both direct photovoltaics and the sun-powered wind and hydro, will likely be sufficient for civilization's energy needs. We're learning to tap the power source that's sustained life all along, not through the inefficient intermediary of ancient buried plants, but directly converting photons to electrons at the point of collection. It's elegant, appropriate somehow, that the species that evolved under the sun's light is learning to harness it deliberately. The sun in cosmic perspective. Stepping back now to see the larger picture. The sun is a star, one of approximately 100 billion stars in the Milky Way galaxy, which is itself one of hundreds of billions of galaxies in the observable universe. The sun is not special cosmically. It's a G-type main sequence star, spectral class G2V, surface temperature about 5,800 Kelvin, luminosity about 1 solar luminosity by definition since it's the reference standard, mass about 1 solar mass, similarly by definition. There are stars much larger than the sun, blue giants and supergiants dozens of times more massive, hundreds of times more luminous, burning through their fuel in just millions of years rather than billions. There are stars much smaller, red dwarfs 1/10 the sun's mass, 1,000th its luminosity, but far more numerous than sun-like stars, and they'll shine for trillions of years, their fuel consumption so miserly they'll outlive the universe's current age many times over. The sun is medium-sized, middle-aged, medium temperature, unremarkable in almost every measurable way. But it happens to be our star, the one we orbit, the one that makes Earth habitable. That's its only special quality. It's ours. And it's placed correctly, and it's stable enough that life could evolve in its light. The sun contains 99.86% of the solar system's mass. Jupiter, the largest planet, contains most of the rest. Earth and the other terrestrial planets are rounding errors, tiny remnants left over from the sun's formation. The planets formed from the protoplanetary disk, the flattened cloud of gas and dust surrounding the young sun. Solid particles collided and stuck together, growing into planetesimals, then protoplanets, then planets, sweeping up most of the remaining solid material in their orbits over tens of millions of years. Earth formed at approximately the right distance for liquid water to exist, in what's called the habitable zone. Too close to the sun and water boils away like on Venus. Too far and it freezes like on Mars. Earth got lucky, or we wouldn't be here to notice. The anthropic principle suggests our observation of this lucky placement is inevitable. We could only evolve on a planet in the habitable zone, so of course we find ourselves in one, though this doesn't explain why any habitable planets exist at all. The sun's gravity holds the solar system together. Planets orbit in ellipses, following Kepler's laws, which follow from Newton's law of gravitation, which can be derived from general relativity's curved space-time. The mathematics is elegant. Planets don't orbit because the sun attracts them, precisely, but because the sun's mass curves space-time, and planets follow straight lines through that curved space, which appear as elliptical orbits in our reference frame. It's the same mathematics that describes Mercury's orbit precessing slightly, a relativistic effect that validated Einstein's theory. The sun's light defines where life can exist in the solar system. The habitable zone is currently from about 0.95 to 1.5 astronomical units. Earth's distance is 1 astronomical unit by definition. But remember, the sun is slowly brightening. Early in Earth's history, the sun was dimmer, and the habitable zone was closer. In the far future, as the sun brightens toward red giant phase, the habitable zone will move outward, eventually beyond Earth's orbit, making moons of Jupiter or Saturn potentially habitable for a brief astronomical moment before the sun swells into red giant phase and renders the inner solar system uninhabitable entirely. There's something profound about understanding all this while still experiencing the sun subjectively, the way our ancestors did. You can know that the sun is a sphere of plasma 1.4 million kilometers in diameter, containing 10 to the power of 57 atoms, fusing 600 million tons of hydrogen per second, outputting 3.8 times 10 to the power of 26 watts, with a surface temperature of 5,778 Kelvin and a core temperature of 15 million Kelvin. 8 Kelvin. You can know all this, and still when you step outside on a sunny day, it's warm and pleasant, and the light makes everything visible, and it feels good. The subjective experience hasn't changed. The sun rises, arcs across the sky, sets, the cycle repeats. Seasons change as Earth's tilted axis points toward and away from the sun during its yearly orbit. Summer is warm because the sun's rays hit more directly, and daylight lasts longer. Winter is cold because the rays are oblique and days are short. These patterns have repeated since before humans existed, since before life existed, since Earth formed and began its endless orbit. From ancient worship of Ra and Inti and Sol Invictus, through Greek philosophy and Islamic astronomy, through Copernicus and Galileo demoting Earth from the centre, through spectroscopy revealing solar chemistry, through Einstein and Bethe revealing fusion as the power source, through space-age observations from above the atmosphere, through modern understanding of stellar evolution and solar physics, the journey has been from mystery to knowledge, from fear and worship to understanding and measurement. But understanding doesn't diminish wonder. If anything, it enhances it. The sun is more remarkable, not less, for being understood. That nuclear fusion at 15 million degrees in the core can produce exactly the right steady luminosity to warm Earth perfectly, that this has continued for billions of years and will continue for billions more, that we're here at the right time in a universe 13.8 billion years old, that we can understand any of this at all. These inspire awe deeper than ancient worship ever could. The sun shines on. It shone before humans evolved. It will shine after humanity is gone or transformed beyond recognition. It shines now, patient and steady, indifferent to observation, following the laws of physics that govern all stars, all galaxies, the entire cosmos. We depend on it absolutely. We understand it increasingly well. We're learning to harness its power directly, and still, on a clear morning, watching sunrise, the subjective experience is one of light and warmth and gratitude, the same response our distant ancestors felt when they didn't know what the sun was but knew they needed it desperately. It is late now. The sun has set wherever you are, or perhaps it's rising, or perhaps it's noon and blazing overhead. Somewhere on Earth it's always noon, the sun always at zenith, the light and heat at maximum. Even as somewhere else it's always midnight, the sun below the horizon, its light reaching that location by reflecting off the moon, or not at all. The Earth turns, the sun shines, the dance continues. Somewhere in the sun's core, protons are fusing into deuterium, the first step in the proton-proton chain, beginning a journey that will take 100,000 years before the energy reaches the surface and radiates into space. Some of those photons will reach Earth 8 minutes after leaving the sun's photosphere. Some will warm someone's face. Some will be captured by a plant's chlorophyll, beginning their conversion into chemical energy that might eventually become part of someone's lunch, the solar energy transformed into biological energy, powering muscles and nerves and thoughts. Some photons will hit solar panels, be converted to electricity, power lights or computers or electric cars, human technology learning to capture and use the solar power that's always been there. Some photons will simply warm ground or water or air, contributing to the great thermal balance that keeps Earth habitable, the energy arriving from the Sun exactly balanced by energy radiated back to space, maintaining the delicate temperature range where water is liquid and life flourishes. The neutrinos from fusion in the core are already here, passing through Earth right now, billions per second through every square centimetre, ghostly particles that barely interact with matter, streaming outward from the Sun at light speed, most passing through Earth without touching a single atom, continuing into interstellar space, carrying direct news of fusion reactions that happened in the core 8 minutes ago. Unlike photons, which take 100,000 years to diffuse from core to surface, neutrinos escape immediately. They're a real-time window into the Sun's heart, proof that fusion is happening now, confirming theory through observation. The solar wind flows continuously, the Sun's corona expanding outward faster than the Sun's gravity can hold it. Charged particles streaming through the solar system at hundreds of kilometers per second, forming the heliosphere that extends beyond the orbits of all planets, eventually meeting the interstellar medium at the heliopause more than 100 astronomical units from the Sun, where the solar wind pressure equals the pressure of interstellar plasma, where the Sun's influence finally fades. Rest now. The Sun continues its work, tireless and patient, nuclear furnace at the core, converting mass to energy, energy diffusing outward through radiative and convective zones, emerging as light from the photosphere, warming planets, making life possible, shining steadily as it has for aeons and will for aeons more. From ancient mystery to modern understanding, from God to fusion reactor, from the centre of the universe to one star among billions, the Sun remains what it always was, the source of light and warmth, the giver of life, the steady presence in Earth's sky, burning brightly through cosmic time. Sleep now, while the Sun shines somewhere, always somewhere, the Earth turning, the light moving across the planet's surface in the eternal cycle of day and night. The fusion continues, the photons journey outward, the heat radiates into space, and tomorrow the Sun will rise again, as it always has, as it always will for longer than empires or species or even continents endure. The ancient priests were right to honour it, even if they didn't understand it. We understand it now, and it's no less worthy of wonder. Rest easy, under the light of our star.